right? Oh wait, no, we thought said indigo or violet.
Okay, relax. I didn't have the electromagnetic spectrum with me.
And neither do I.
Well, yeah, but you don't know what you were doing. Come on.
What? I don't know what I was
You
doing.
weren't even able to. You said you couldn't do it without a calculator.
Okay, but I actually persevered. I actually did it.
We finished today's lesson. As you saw that as a teacher, what percent of the work did I do? 0%. If you are a teacher and you have to do more than 0% of work, then you are not a teacher. You should find another job. Okay, now both my students, I don't know who did more than 50%, but my target, my goal was that Isaac should be doing 50% and Raf should be doing 50% because that's what it is. Okay, Isaac, what did you discover today?
So today I discovered the concept of energy levels, so how an electron can gain or lose energy based on where it is in the atom. And I also discovered that whenever an electron gains energy, it has just absorbed light, and when it releases energy by jumping down energy levels, then it emits light. And we were able to find the color and frequency and wavelength of that light just by knowing the energy of the electron that jumped down.
Oh, what did you discover, baby?
Yeah, I discovered that an electron that jumps from n equals 4 to n equals 2 emits not violet light, but blue light.
Thought, again, I don't want to put words in your mouth. I thought you both gonna say that, we probably saw 13.6 as a child.
Yeah,
okay,
so
so
I can talk about that.
yeah, sure.
So I never knew we discovered how to derive 13.6 electron volts just using kinetic energy and potential energy.
Everybody, welcome to our physics class. Today our topic is energy inside the atom, okay, especially energy associated to electron. When you look inside the atom, what do you see? You see electron, proton, and neutron. Of course, you see hadrons and leptons, which is electron, and mesons and baryons and quarks and so on, right? We are talking about leptons today, and the most famous lepton is electron. We're going to try to understand where 13.6 electron volt come from. Negative 13.6, so negative 2.17 times 10 to negative 18 joule come from. That is the energy of electron on the ground state, energy of hydrogen. Two, we invited two students to help us understand. Can you introduce yourself?
Hello folks, this is Rifat Bari, Brown University graduate student.
And my name is Bohr, and I'm doing my bachelor's in math and physics at NYU.
I have some challenge for you and challenge for the Brown student. You have pen and pencil, right? Okay. Now, Isaac, can you construct the Bohr model for hydrogen with 1, 2, 3, and 4 radius? Go ahead, on the board.
Here's the thing. These electron shells slowly get closer and closer to one another. So here's the second electron cell. And if we were to excite the electron, it would jump up from cell 1 over to cell 2. And then the third one is even closer together. So it would jump up from cell 2 to cell 3, which is a smaller jump. And then the fourth cell is even closer. And at some point, as the cells approach infinity, it converges on one finite radius. And that radius is actually somewhere over here.
Thank you so much. Raf, can you write N1? Where is N1?
N1.
Can you write N2? What about N3? N4? All right. What about E1? Where are you gonna write E1?
E1 here.
Okay, exactly same where N1 is. And E2?
Here.
And E3? And E4? What about E infinity?
All the way when it's ionized.
Okay, very good. Now this is two-dimensional hydrogen atom, right? Why this is an hydrogen atom?
There's no neutron, only one proton.
Okay, so this is a hydrogen atom. Can you write the symbol for hydrogen atom?
Yes.
All right. Can you now convert this one to 1D? Okay, that's good.
Ground state.
And one, okay, yeah, I want you to do 4.
Okay.
13.6 electron volt.
Mhm.
Okay, good. All right, and then N2.
Okay.
You don't have to exactly draw to the scale.
Okay.
Okay, Isaac, you are on the camera.
And
Okay, and 3.
and 3.
And finally N4. So make sure you write and okay, make sure you write N infinity as well. N infinity, you can exaggerate it a little bit, and E infinity is equal to 0. Okay, very nice. Okay, Isaac, can you come over here? Only one shell. Hydrogen with only one shell.
One cell is more than enough.
Okay, and you're gonna show me a few things. Centrifugal force. Show me first centrifugal force on this hydrogen atom.
Okay, so the centripetal force is,
Don't
of course,
block. Don't block.
going to be pointing in this direction towards the center of the nucleus. And while some may say, oh, that's the force of gravity, while it is still present, it's so small compared to the electrostatic force that it might as well be non existent. So,
Now hold on. Okay, centrifugal force you wrote. What is the gravitational force? Which direction is the gravitational force between these two objects?
it's in the
Two
same
bodies.
direction, but it's so small that we need not even consider it.
Isn't gravitational forces both direction? Gravity.
Well, yeah, but
Yeah.
we're only drawing forces on the electron.
Okay. All right. Number 3. Can you show me the velocity of electron? What is the velocity vector?
Well,
Direction of velocity vector.
that would just be the tangential velocity, which would look something like this for the
Right, V,
corresponding
velocity.
electron.
Actually, that violates the uncertainty principle.
Yes,
because
I know.
If you draw the electron here, then you don't know which direction the velocity.
I know. We're working with the Bohr model, not quantum mechanics.
we're gonna keep the velocity.
If we're talking about
that's right. We're gonna keep.
If we're talking about quantum mechanics, then this whole model is invalidated anyway. You
But-
might as well just erase
Yeah,
it.
but can you? This is Bohr model, by the way. The quantum mechanics really came from Bohr model. All right. Can you justify the fact that the centrifugal force and velocity vectors perpendicular with each other?
Basic physics. Sorry. So
No, where they should be perpendicular, but why the velocity vector doesn't look perpendicular with respect to that?
sorry. There we go.
Okay, Raf, do you have any question now so far?
No.
All right. So
Make it easy.
Okay, what is the potential energy? Why there is a potential energy now? Explain.
Okay. So think about
No, that is space you need for something else. Right, potential energy.
think about an object blasting off from Earth, right?
Right.
So think about its gravitational potential energy minus gmm over r. So that means that it actually technically increases as r goes up. Why? Because even though the magnitude decreases, since there's this handy negative sign, that means that the total. So it's actually in total going up. Same thing is happening here. If you look closely, we're going from 13.6 to 3.4 to 1.8. So I guess smaller, but technically, since there's a negative sign in front, the electron is gaining energy. So, in the same way, if we have this object blasting off from Earth, it's actually gaining energy by going farther and farther and farther.
All right, then let me
And
ask
so-
you one question. You have N1, N2, N3, N4, and infinity. Where is the maximum energy and where is the minimum energy?
Well,
No, circle it. Put a circle on N. Put a circle on the end that you think had maximum energy.
well, maximum energy is at n equals infinity.
Okay, put a circle at N equal infinity.
As you can
Put a
see here.
circle on the end that has a minimum energy.
This one right here, n equals 1, and the same thing goes for this.
There's a better way to draw it. Can I draw it?
Oh, please, man.
Okay, I just want to show.
Yeah,
Can I
sure,
draw it?
sure.
I'll just draw
Okay,
it.
Isaac, you can go back to desk.
Should I draw it here or?
No, you can stand up.
Okay. So
No, you need that is okay.
I'll erase it.
Erase it. Okay, good.
So you can depict it as follows: energy versus radial distance. Right here is the proton, or if you want the Earth, and here is what the energy curve looks like.
People do not
So-
understand that, bro.
For example,
No, that's why we are making this video.
For
Okay.
example, when if you are considering the potential energy of the Earth, then this is minus gm over r. Let me explain. So, if you are very far away from the Earth, then the potential energy is almost zero. As you get closer and closer to the Earth, potential energy gets bigger and bigger, but smaller because it comes with a negative sign. So that's why the energy is decreasing. And in the same way, you can consider the energies of the hydrogen atom like this. So when you are in the ground state,
Okay, 13.6 electron volt,
So-
minus 3.4. Where did minus 3.4 come from? Oh, N2 minus N1. Okay.
yeah, 1 over n squared times 13.6. So if we're on the second energy level, then n is 2. So minus 13.6 over 4 gives you minus 3.4.
Right.
So when you're at the ground state, then the energy is minus 13.6. When you're at the first excited state, then the energy is minus 3.4.
That's right.
Next one, minus 1.8.
And
So-
it's approaches to zero.
And it approaches.
But never be zero.
Never is
So
asymptotic.
it's asymptotic. Okay. All right, very good. Now, Isaac, yeah, it is. Isaac, can you tell me where this hunky funky 13.6 come from?
Okay. So back to the point, we have U equals minus G.
Now, start from top.
We have U equals minus dmm over R. Now, if you've already done a little bit of electrostatics, you'll
can
know.
you use white chalk? This chalk is not visible. Can you actually start with Coulomb law?
Starting off with this, you may know, if you've already studied a little bit of electrostatics, that regular gravity is actually quite analogous to the electrostatic force dictated by Coulomb's law. And in the same way,
What?
these aren't analogous.
Analogous? Yeah, that's right. But which one is bigger?
What? No, I'm not making a point about which one is bigger.
Okay.
So
We'll use this chunk.
But can you answer that question? Which one is bigger?
obviously, the electrostatic force on the scale that we're on, because
Can you make a assumption how much bigger it is? What
Probably
order
like-
of magnitude?
probably like 8 orders of magnitude.
39.
Oh, cool.
39 order of
10
magnitude.
to the 39 times bigger.
Oh, cool. Okay. So we have that gravitational potential is minus dmm over r, and in the same vein, electric potential is going to be minus kqq over r. So what that essentially tells us,
There's no minus sign on the electric one. It's just kq over r. Because
No, there is minus sign. Yeah.
No,
Okay.
that
The potential energy you have to keep the minus sign.
just wait and see, buddy. Okay.
fine.
All right. So now all we need is the distance from the proton to the
How
electron in the
much?
ground.
What is the radius?
511.
5.53 times 10 raised to negative 11 meters.
5.53 times 10 to the minus 11 meters.
Yeah, that's not a big distance. Meter.
Yes, okay. So now let's plug that in. This is going to be minus 9 times 10 to the 9. This proton charge is 1.6 times 10 to the 19.
You can put a square. The square.
Minus 19.
Doesn't-
Minus 19.
Yeah.
We've had
10 to the minus
It
19.
doesn't matter. Calm down.
Okay.
No, it's minus
Calm
19.
down.
Yeah, it's the charge is
fine.
minus 19, baby.
Okay.
No,
Then-
charge is minus 19.
Then we have to remove this.
No, charge is minus 19.
Yeah. So we get a 1.6 times 10 to the minus 19.
No, you are
minus
not listening.
What the
Char-
hell?
Charge is not
Oh,
Yeah. I was thinking I forgot some physics.
the other minus is not as important as this minus.
Yeah.
okay. And we divide that by r. So, in the end, we get 9 times 10 to the
I have to
9,
have a calculator.
2.56 times 10 to the minus
I don't know why
38.
you're doing this. You should have a
Because
grand equation.
Because I have a bigger brain.
No, please not to say that this is for a student.
Okay, so let's see, what does it come out to?
9 times
2.56
divided by
5.5.
We can already predict what order of magnitude it'll be.
4.16.
Yeah.
Okay, 4.16. Give it 1 second. 9 minus 38 plus 11. That's going to be minus 18.
Okay.
That's not Rydberg's constant.
No, that what that
Oh.
this is not the energy is on the ground state is negative 2.17.
Yeah.
This is not negative 2.17.
This is just the electrostatic energy, potential energy. What other kind of energy does the electron have?
Kinetic energy.
Oh, right.
Kinetic energy.
So let's do the kinetic energy.
How can
All
you
right.
find?
So can you copy that? Put it over here, so we
Oh.
don't forget. Negative 4.16. No, put it over here so we can. All right, erase it.
Okay.
Erase it. Now find the kinetic energy. Start with Coulomb's law. See, you don't have to erase this, but okay. This is our diagram.
Where else are we supposed to
Over
go?
there. This thing. Erase this thing.
Kinetic energy is always positive.
Hold on.
Right?
Kinetic energy. Start with Coulomb's law.
Okay, so now we find the kinetic energy because, as we stated before, the centripetal force has to be equal to the electrostatic force. So by Coulomb's law, the electrostatic force is kQq over r squared, and the centripetal force is mv squared over r.
Good.
And as you can see, we are obviously solving for v. So we cancel out the r's on both sides over here. M is ridiculously small. For an electron, it's actually, I believe,
No. Before you do that,
9.1.
before you plug in the value, can you first get the equation?
It's mv squared is equal to kqq over r. So v is equal to the square root of kq.
I had other plan.
What?
So you're gonna write e, and then you can write half mv half and multiply both sides by half. That way you're gonna get a better equation.
Oh, right, I see. So we write half mv squared is equal to kqq.
Not qq, k is squared. Oh sure, qq is fine.
kqq over 2r. And as we can see on the left side, we've now obtained the expression for kinetic energy, which is this constant, our first elementary charge, our second elementary charge.
At this time, the minus it doesn't matter,
So
right?
it mattered in the first one, but not in the second one?
No.
How does this make any sense?
Can you explain why minus doesn't matter here?
Well, kinetic energy is always positive. You
That's
can
right.
never have a negative kinetic
So
energy.
it just magically goes away then.
Yeah, that's right.
Yeah.
Okay, and we divide that all by 2 times the radius, which is 5.53 times 10 to the minus 11.
Don't calculate the order of magnitude. Isaac
So
can do order of
calculating the
magnitude by
order of
himself.
magnitude, we have 9 minus 19, which is minus 10, minus 29 plus 11 is minus 18.
All right, just do the A. He did the B.
Is this 5.53, right?
Yeah.
Yes.
Okay, 2.08.
Okay, so we've got 2.08 times 10 to the minus 18.
All right,
Now
so you have
adding
a
our two
potential
together,
energy.
which is minus 4.16 times 10 to the minus 18,
Is that
we
give you
get
magic number?
minus
Yeah, look.
2.08.
Exactly.
Big
Congratulations.
That's not.
is minus 2.17.
Huh? 1.7.
Yeah.
Oh, really?
What did you lost that?
There's a percent error.
Okay, sure. Minus. Okay.
No, I think you made a mistake. Okay. So
No, it's a percent error. No, don't forget to write joule.
Okay. And of course, now to get the iconic value all we have to do is convert into electron volts. And all that requires
Yeah, you can do it
is
at the top.
You just have to divide.
we fast. Don't have to patronize me.
Okay.
So to convert from joules to electron volts, of course, 1 joule is just 1.6 times 10 to the minus 19 joules is just 1 electron volt. So all we need to do is take our magic value and divide it by 1.6 times 10 to the minus 19, or 16 times 10 to the minus 18. So all we get is, wait a damn second, no, sorry, 10 to the minus 18 over 1.6 times 10 to the minus 19. And of course, we can take this and make it 0.16 times 10 to the minus 18. So that gives us 2.08 divided by 0.16, which is
1.298 or
no, it's
1.3
not. No, it's not.
because there was a small error.
It's a 0.16, not one.
I mean, you know what I mean. Yeah.
You're stupid.
It says just we got 13 electron volts.
This is 12.94 eV. So of course there is a small amount of error, but this is where 13.6 electron volts comes from.
Good. Raf, show it another way of getting 13.6. Quickly.
Okay.
I want you to get an equation that gives you negative 13.6. Quickly. Okay, you sit down.
Are we going to be doing the whole light thing?
No.
What do you want me to do?
Okay, go to the Coulomb's law. Write Coulomb's law.
Okay. Okay.
All right. F you should be replaced by MAC.
Okay.
Okay, so KE square over R square.
Okay. K, how much?
KE square
KE square.
over R square. MV square over R.
Okay.
All right, now you have
So,
half MV square is equal to
okay, 1/2 MV square is equal to K squared over 2R.
okay, write that.
Okay, so KE is KE squared over 2R.
All right, good. Now potential energy, right? Potential energy is equal to
K
not K, not KR. Potential energy is potential energy is KQQ over R.
Oh, yeah, sorry, yeah. That's right.
So negative, don't forget. So KE square over R.
Okay.
All right. Take the difference between potential and kinetic.
Okay. Oh, very nice. Yeah. KE plus KE
Is equal to negative
So,
negative half KE square over R.
K squared over 2R minus K squared over R.
So it's just negative KE square over R.
Mm-hmm.
That's the equation. Okay. Erase everything. So if you have the equation, then you're not gonna have to compromise with anything. It's not gonna be 12.94. Now it's
Yeah.
gonna be exactly 13.26. 13.6. Why is that? Because you now have less
Right.
worry about the decimal.
And,
5.53 times 10 raised to, okay. Isaac, yeah, I want you to use the decimals. Where is the phone? Yeah, use the decimals. He can do order of magnitude.
Okay,
So
9 minus 38. 9 minus 38
minus 29. Minus 29 plus 11.
You get 4.17.
Minus 18. Okay.
17.
What the heck?
Are you sure you did it? You forgot to square it, probably.
No, I didn't.
Yeah. The confidence strikes again. No, 1.6 squared is not. Can
1.6 squared and not 2.56.
Then can I see what you did?
No, hold on. I mean, why attacking? It's just try to see where things went wrong. So
Why
9.
did things go? How did things go wrong?
Oh,
It should be. It should be two. It should be 2.17.
You guys only calculated the
Yeah.
potential.
hey, no.
No, we did the other one.
You did not sum the kinetic.
We did.
And P is K.
We did some the kinetic.
Why do we get the exact same answer as we got for the potential then?
Oh.
It seems that you forgot something.
Oh,
Huh?
yeah.
What did you forget?
To sum the kinetic energy.
Over here. Because
Oh, you
one
didn't
half-
put 2?
Yeah, 1/2 minus 1 is 1/2.
So you didn't put that?
I didn't put the 2.
Oh, god
This
damn
would be
it. Yeah.
times-
Yeah, it's a half. I said it like 50 times.
So
Yeah.
that gives us 2.08.
Yeah, that's it. That's it. 2.08.
Okay.
Yeah.
2.08 times 10 to the minus 18.
Okay. And Joule. And that gives you 13.6 electron volt.
Yeah, not 12.94.
Yeah.
Okay.
Very
All right.
nice.
Good. Now again, it's competition time, right? Whatever they learn, they're gonna put that in action. So I'm gonna let the electron fall, right?
Oh, wait. My second.
Yeah, I'm gonna let the electron fall, and they're gonna find what type of light the electron will emit. Okay. So go sit down. Energy level for hydrogen. So draw N1, N2, N3, N4, N5, and N6. You don't. All right. Let the electron fall from N4 to N2. Hold on. Don't study yet. All right. Isaac, can you explain what happened when electron falls from N4 to N2?
Well, when an electron falls, essentially an electron gets excited and goes up to this energy level because it absorbed a photon or a light wave. And so, once it releases that, it's going to release a photon with varying frequency.
Okay.
Is
So now, Raf, can you tell me, as Isaac said, is going to release energy?
Yeah.
What that energy we human perceive as?
Light.
That light has color?
It depends on which level it lands on. If it lands on n equals 2, it'll release visible light. But if
Find that visible light.
what
Go.
the hell? Are we allowed a calculator?
No. No.
What?
There's no calculator.
How do I multiply
okay, that's fine.
2.17?
I'm okay with that. He doesn't know how to do it, but I know.
God, insane.
Okay.
What is he doing? Just gonna set this to 2. Okay. And this is okay. So this is the and then we multiply that. 6. How much is that? It's like 60.
Go
Okay.
to all the way to nanometer.
And we
I want nanometer.
and now we have to do this. And the only thing I can do is another cheap approximation. So I'm gonna do. I got it. I got it.
Wait for him.
We think something weird. This is what I got for the frequency.
That is not what I got for the frequency.
That doesn't mean Isaac is right. We'll find
Oh,
out
this
soon.
is plus. Oh, sorry, this is plus.
Okay.
So 1/60. So this is my, this should be plus. So,
Don't check the internet.
In the
yet.
meantime, I'm pretty sure this is supposed to be red. So I'm gonna go with that. But wait, let me think for a second. Okay. As wavelengths get
yes.
No, I need nanometer. Sorry.
we get
I
gamma,
need nanometer.
ultraviolet,
Okay.
violet.
Okay, so this should be plus.
So what range is?
Okay, so 14.
Yeah, I guess I'm just gonna have to guess. I'm gonna guess green.
Alright, 480 versus 500. Okay, Isaac, guess the color.
Green.
Albert, guess the color.
Can I justify?
No, just guess the color. You're gonna check
Okay.
internet.
Okay, I'll guess. Roy, G.
Isaac, also you can do that.
Okay, I know that blue is the standard 500
He
nanometers.
innately
So
knows.
480 is less than that, so we're heading towards the higher end of the spectrum, which means that we have to have either indigo or violet. So I will, since it's only a little bit shifted, I will say indigo or purple.
Never mind. I think I'm gonna say blue.
How the tables turn.
Refast, how would I know?
Alright, now we're gonna check the internet. Okay. Live internet. Live.
Ready?
Mm-hmm.
Okay. What? Whose one is correct? You want to put 480 or 500? Which one?
Oh, fast do 500.
Okay. 500 nanometers. It should be blue.
Show me.
Cyan.
No, I want the Google. No, put it on Google. 500 nanometer is what color?
Cyan.
Good.
Cyan is between what?
Green and blue.
Okay, green and blue. Okay, so when he wrote green, he was very close.
And when I wrote blue,
Okay.
I thought
Wait, what? I thought 480 was.
And I will check 480.
Oh, okay, 480 nanometer color.
480 must be pure blue.
Let's see what color is 480
Nanometer.
What? It says blue.
Yeah, blue has it. Okay, now the big one.
I'm pretty sure violet is like
Hold on,
750.
hold on. When the electron jumps from
No, not
N4,
750.
hold on.
300.
Now, hold on, you're not done. Write down when electron jump from N4 to N2, what color does it emit? Write it down on Google,
Oh.
because I still don't know whether it's 500 or 480.
Well, we could have used the actually correct values.
No, check it out. What color does it emit when it falls from N4 to N2?
Refast one is possibly more accurate, but blue.
Blue, because how much?
Damn it. So I guess we're both